Alright, so in this video, I want to go over kind of how we can treat mixtures of gases, how we can use them in chemical problems, and ways that we describe like really solutions of gases, right? So as we saw previously, any gas mixture is going to homogeneously mix. So unlike, maybe something like oil and water, right, where those two things don't mix, and you have like these different regions of oil and water, right? With a gas, you don't really have those different regions because they're all just individual little particles. They're not really like in these condensed phases where you could potentially, see the divides between them. But then kind of going further than that, right, when we think about how these gases are going to mix together, right, because they have so much space in between them, they're not really going to interact with each other. So again, this is different from like a condensed phase substance, which you would learn more about in Chem 162, right? Those will have actually interactions between the different chemicals in the mixture, right? Between those different substances. For gases, because they are so spread apart from each other, it's as if they don't even know that the other gas is there. And so they're going to behave just the exact same way as if it were a lone gas. So, right, what I mean by that is like consider here I have a mixture of helium and argon, right? And so I start with my just plain helium in a canister and it's doing its gas thing, right? Moving around, exerting some amount of pressure on its container. And in another container, I have a bunch of argon and it's doing a similar thing, right? Bouncing around, making pressure, all of that business. And if I were to mix those two together, right, into the same size container, there's literally nothing different about them, right? The helium is not going to interact with the argon. It's not going to be affected by the argon's presence. They're both going to keep doing what gases do and keep, exerting pressure like we know them to. Of course, this isn't going to be the case if those gases happen to undergo some kind of chemical reaction, right? Then that's not necessarily a mixture, that's like a chemical combination. But if we're assuming, that no chemical reaction occurs, then this is what we would see, right? It would be just the same as if we had those gases individually. We're just kind of combining them together, and nothing really changes in their behavior. So to be a little bit more precise about that, right, what I mean by their behavior isn't changing is like the way that they exert pressure on their container is not changing. Now I want you to pay closer attention to like the numbers with each of these canisters. So right in our first container filled with helium or the little blue atoms, that has a pressure of 2 atmospheres. In the second container filled with argon or the little purple atoms, right, that had a pressure of 4 atmospheres. And when I combine them together, right, the pressure of the helium itself is still 2 atmospheres, and the pressure of the argon itself is still 4 atmospheres. So, right, that's what I mean by the behavior doesn't change by mixing these two, right? They're still exerting like the same pressure that they would have when they were lone gases, right? When they weren't in the mixture. And so now that I've combined these gases, right, what we call those individual pressures that the helium exerts or that the argon exerts, right, that's called a partial pressure because that partial pressure is now contributing to the total pressure of the entire mixture. So, right, you can see just above the furthest right canister, the total pressure, or P total, is equal to 6 atmospheres, right? It's equal to the sum of those partial pressures. Now, this idea is referred to as Dalton's law of partial pressures. It's defined like so. When you have like a mixture of gases, the total pressure that that mixture exerts is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, and so on and so forth, right? You could have really like infinite gases mixing together, and their partial pressures summed together would equal the total pressure of the mixture. But so let's see some other like ways that we can maybe describe gas mixtures, not just by like their partial pressure, but through some other representations as well. So first, right, let's consider a mixture of N2 and H2 gas, right? Nitrogen and hydrogen, both diatomic elements. I'm not being specific here about the mixture itself, right? I'm trying to keep this generic here. But right, if I have some nitrogen gas, its pressure is equal to the moles of nitrogen times the ideal gas constant times the temperature divided by the volume. And if we have some hydrogen gas in that same container, right, it's going to have the same ideal gas constant because that's always constant. But in the same container, it has the same temperature, the same volume. What's really only different about these two gases, my nitrogen and my hydrogen, is the moles and therefore the pressure of each of those. Right? And so I've kind of written out here how we could define each of these gases' partial pressure in terms of their moles and then in terms of all those other variables as part of the ideal gas law. And so with this, right, I could then write out the total pressure of my mixture as the sum of the partial pressure of N2 and the partial pressure of H2, right? So that's written out in this equation right here, where P total is equal to both of those pressures that we had above now added together. And what we can kind of do with this, right, is factor out all of those same variables. In this mixture of these two gases, right, they are in the same container, and so they're going to have the same volume and the same temperature as each other. And again, R is always a constant, so that's also going to be the same between these. And so, right, kind of factoring things out here, I can write my total pressure as just equal to the sum of the moles times RT over V, right? So this just kind of simplifies things. So if you have, say, a big mixture of gases and you know how many moles of one gas versus how many moles of the second gas, a third and fourth gases, right? You don't need to go and solve the partial pressures of each of those individually and then add, right? You could instead sum up all of their moles and then just multiply that by RT over V. So let's look at an example like this one. So here I have, right, 0.124 grams of oxygen gas, 0.813 grams of nitrogen gas, and 5.162 grams of carbon dioxide gas, all placed into the same 625 milliliter container at 20.4 degrees Celsius. And so what I want to know about this gas mixture is, right, what is the total pressure of the mixture? So again, we'll want to use our ideal gas law, but we can kind of take some shortcuts in it, right? Rather than solving for like the partial pressures individually, we can find the total pressure by using the total moles as our N value, and then again, just having the rest of the ideal gas law like pictured. So go ahead and take a few minutes to work on this one, right? We want to find the total pressure in atmospheres of the mixture, and we'll go over it in just a minute. Okay, right, so in order to solve this one, what we're going to need to do is use our ideal gas law like we usually do. It's just instead of one type of moles, right, in our N value there, we're going to find out the moles of the oxygen, the moles of the nitrogen, and the moles of the carbon dioxide, right? So I have three N values that I'm essentially going to need to find first. Then I can sum them all up and have my total moles of the entire gas mixture. But so that shouldn't be too hard, right? With the information that we're given, we have grams of each of these gases. All we need to do is convert those into moles. So right, we're going to use our good old molar mass technique, right? For the oxygen, I have 0.124 grams divided by 32 grams per mole, right? Remember that oxygen is diatomic, so that's two oxygens in the molar mass. And so the oxygen alone contributes 0.003875 moles of oxygen. Likewise, doing the same thing for nitrogen, I got 0.02901 moles of nitrogen. And for carbon dioxide, I have 0.11729 moles of CO2. And to find my total moles, I'm just going to add them all up together. So right, adding each one of these. And so when I do that, I get 0.15018 moles in total. And technically that is to four significant figures, right? So if we look at our different sig figs that we started with, yes, we had a couple of masses that were only 3 sig figs, and therefore the moles of those were only 3 sig figs as well. But when we add together, right, we're going by decimal place, and it looks like kind of our lowest decimal place is to the 10,000th, or 4 past the decimal point, and so we should report this to 4 past the decimal point as well. Now, when I put all of these together back into my kind of total ideal gas law right up at the top here, right, so I have my moles, I have the temperature now in units of Kelvin, so we started with 20.4 degrees C, I just converted that into Kelvin, and then the milliliters for the volume I turned into liters, and so we have the following setup. I didn't write out R this time because it's just like so long and takes up so much space, but right, R is just again the same ideal gas constant that we've been using. And so solving for this, I got 5.79 atmospheres, right, just 3 significant figures because the volume itself was 3 sig figs. But so, right, this is a little bit quicker than if I were to like go through and solve for the partial pressures individually for these different gases, right? I could do things that way. I could find the partial pressure of N2, the partial pressure of O2, and the partial pressure of CO2, and then just add all those up. But kind of like factoring out here, right, all of the variables that are going to be the same for all of those, like the volume and like the temperature, right? This just kind of saves us a little bit of time. But so, right, let's kind of take this a little bit further, right, and go back to kind of our more generic example of just the nitrogen and hydrogen, right, written out symbolically here. If we kind of think about the individual moles of each gas as being like part of the total moles, right, what that means then is that like each gas is contributing some fraction or some part of the total. And so we call that the mole fraction, or just as a symbol, a capital X. So for instance, the mole fraction of N2 from our previous example of nitrogen and hydrogen mixed together, right, it has a mole fraction that is the moles of N2 divided by the total moles, right? Or written out right here is just, N of N2 divided by the N's summed together. And so mole fraction is kind of similar to, what we had seen way earlier in the quarter with mass fraction and like mass percent, right? This is the same kind of idea. It's just really thinking about, what percentage or what fraction of the total moles is taken up by an individual substance. And so just like the mass fraction and mass percentage that we saw previously, we may also kind of use mole percent as another way to kind of link mole fraction, right, where instead of having a fraction as, something between 0 and 1, right, the mole percent is something between 0 and 100%. But just like previously with the mass fraction and with the mass percent, when you add up all of the mole percents for every substance in the mixture, right, it should sum up to 100%, or all of the mole fractions should sum up to 1 so that everything is accounted for. Right, so with something like a mole fraction or mole percent, right, we can kind of connect, again, partial pressures to total pressures through this equation here. So, right, what this equation says is that the partial pressure of some substance, which we'll just call A, right, gas A, its partial pressure is equal to its mole fraction times the total pressure. So, right, again, this is very much connected to the previous equation that we saw of like the total moles times RT over V, right? This is just kind of a derivation of that. But so consider here this example where I have a mixture of nitrogen and oxygen gas, and the mixture is 79 mole percent nitrogen and has a total pressure of 0.75 atmospheres. So my question for this mixture, right, is what is the partial pressure of oxygen in this case? So right, think about how the mole percent of nitrogen may relate to the mole percent of oxygen, or how the partial pressure of nitrogen may relate to the partial pressure of oxygen. Right, go ahead and take a minute to think through this one, and then we'll go over it in a little bit. Okay, right, so there are a couple different ways that we could approach this problem, but I'm just going to show you one way that I did it, right? You may take a different path, but hopefully you should get the same result here. But right, what we're told is that the mole percent of nitrogen in this mixture is 79. So what that means then is that the mole fraction, or X, of nitrogen is going to be 0.79, right? Just taking that percentage and turning it into a decimal. And so from that, right, I can say that the partial pressure of nitrogen is equal to 0.79 times the total pressure, 0.75 atmospheres. So right, again, what I've done here is I've just taken the mole percentage and I've turned that into a mole fraction and then multiplied by the total pressure. And what that gives me then is that the partial pressure of nitrogen is equal to 0.5925 atmospheres. From there, what I can say is that, well, the total pressure of my mixture should just be the pressure of the nitrogen plus the pressure of the oxygen, right? So those two things are going to sum up together to give me my total pressure. Kind of rearranging that to solve for just oxygen alone, right? I can say that the partial pressure of oxygen is equal to the total minus the partial of nitrogen, right? So because this mixture is just nitrogen and oxygen, I know that any part of the total pressure that isn't the nitrogen must be the oxygen gas. And so I can use the values that I already have of the total pressure and the nitrogen gas and say that the partial pressure of oxygen is equal to 0.75 atmospheres minus 0.59 atmospheres. Or completing that, I got 0.1575 atmospheres, but to 2 sig figs, right, that should be 0.16 atm. And so, right, choice A here is correct. We have 0.16 atmospheres of O2. Right, again, you could approach this maybe a different way. Maybe from the mole percent of nitrogen, you first found the mole percent of oxygen, right, just by subtracting from 100. And then you use that to solve for the partial pressure of oxygen, right? There's a couple different paths that you can take, but they should all lead to the same result, right? So if we do this correctly, we should have a 0.16 atmospheres as our partial pressure of O2. Now, what I want to kind of look over next is like a very particular example of partial pressures of gases. Because, right, like, especially when we're working in the lab and stuff, because we're exposed to like the open air and things, it's going to be pretty hard for us to just have like one isolated gas and not a whole mixture of gases, and even when we try to do experiments where maybe we are just capturing one gas, what ends up happening is we do end up with a mixture. And so here I want us to consider an example that we've actually used previously in experiments, not this exact reaction, but kind of the same method and the same setup. So right here we have what is called a pneumatic trough, right? It's a very fancy word, but basically it's just a gas collection apparatus, and so it works by capturing the gas that may be produced from a chemical reaction or maybe like a physical change, and capturing that gas into some closed container that was initially just filled with water, right? As the gas is produced, the gas is going to displace the water, and so water gets pushed down, and so you are left with then just your gas up above in the chamber. And so we've done this in lab, I think using some less fancy equipment, just like an inverted graduated cylinder, but right, it's the same idea here, right? Just collecting gas by sealing it in with water. And so when we did this in lab, we were able to measure the volume of the gas that was produced just using the markings on the graduated cylinder. Some other equipment may have similar markings or similar ways to determine the volume of the gas that was produced. Now, one kind of key thing that we didn't necessarily account for in our earlier experiment of the hydrogen peroxide and bleach lab was that the pressure inside our gas collection tube should be equal to atmospheric pressure. Kind of thinking back to like the manometers and how, right, you had maybe some gas in a container and it's pushing down pressure, but then on the outside of the container, atmospheric pressure is pushing down as well. And if the atmospheric pressure is stronger than, say, the gas in the container, then that's going to push more of the liquid, in that case mercury, up into the container, right? So that's kind of like the competing forces there. In order for our pneumatic trough to like really work for us, we're going to want to make sure that those competing forces are equal. And we can actually change that by kind of adjusting the height of the collection tube versus the water level outside the tube. We'll see this more in experiment, so you'll kind of get a better idea of that. But kind of what to take away from that is that, whatever the pressure is inside the chamber, we're going to assume that that's equal to atmospheric pressure. So if we have a barometer or something that tells us the atmospheric pressure, then we can know what the pressure is inside our chamber. And so in theory then, right, by knowing the atmospheric pressure, we should know the pressure of our gas that was produced in the reaction. However, right, the gas that's in that chamber is actually not only the gas that's from the reaction, even though it started off with just water in there. So no air, no other gases were in the apparatus to start. Some of the water on the surface in that chamber does actually evaporate and go into the gas phase. So right, even though it's liquid water below, and even though we're not like boiling it by any means, just some of the molecules do kind of jump off and go into the gas phase. And so because of that, they too are going to exert pressure. And so while the total pressure in the chamber is equal to atmospheric pressure, that's not only the pressure of the gas that was produced from the reaction, right? In this example, we were producing O2 gas from this reaction. In this apparatus, right, up above the water is not just O2 gas, but also some water vapor as well. The partial pressure of the water is defined as vapor pressure, and you'll learn a lot more about this in Chem 162, but it's basically the pressure of a gas when it's up above its liquid phase. So right here, because we have liquid water at the bottom of the trough, it's going to produce some gas up above it called the vapor pressure, right? It's partial pressure that the gas is contributing. And because water is, such an important substance, we use it all the time. Similar to how we have like these super precise density values for water at different temperatures, right? We can also find very precise vapor pressure values for water at different temperatures as well. Because as it turns out, right, vapor pressure is going to change depending on the temperature. Again, you'll learn more about that in Chem 162. But so, right, oftentimes we're going to look to literature, look to some reference material to find out the vapor pressure of water at a particular temperature to take into account for our total pressure in the pneumatic trough. But so let's look at one example kind of using a pneumatic trough like this one. Again, we're going to do the same reaction that's been described here as decomposing potassium chlorate, turning that into oxygen gas, and then whatever else, potassium chloride or other substances. But so right in this example, we are collecting oxygen gas, and we find from the experiment that the atmospheric pressure is 728 torr and the room temperature is 22 degrees Celsius. We also find that the volume of the gas in our apparatus is 155 milliliters, and at this particular temperature, right, the vapor pressure of water is 19.8 torr. So right, from all of this information, I want us to determine how many moles of O2 were produced from this reaction. So go ahead and take a few minutes, right, kind of put together all of the different pieces that we have here, right? What we want to find out is the moles of O2 produced from this particular experiment. All right, so to put this one together, right, as is usually the case for this chapter, we're going to need the ideal gas law. Right here, we're asked for the number of moles, so I rearrange things to solve for N, right? N is equal to PV over RT, or pressure times volume divided by ideal gas constant and temperature. And so, right, the first thing that we're going to address here, and really kind of the trickier thing with this question, or what's different from previous questions that we've seen, right, is really solving for the pressure of just the oxygen. Because for the question at hand, right, we're trying to find the moles of O2 alone, and so we're going to want to use the pressure of O2 alone. And so the pressure of O2 alone should just be equal to the total pressure minus the vapor pressure of water. Now, right, the total pressure here is that atmospheric pressure, or 728 torr, and then the vapor pressure of water is 19.8 torr, right? Both of these are given to us, but we kind of have to make that extra connection to know that the pressure of the O2 is just equal to the total or atmospheric pressure minus the vapor pressure of water. Now solving for that, I got 708.2 torr, really just 708 torr, because our sig fig should just be to the ones place here. But, right, torr is not going to cut it for our ideal gas law equation, and so we're going to need to do a little conversion step, converting our 708.2 torr into instead atmospheres. So torr are just the exact same thing as millimeters of mercury, right? For whatever reason, we have different names for them. So our same conversion factor applies, right? 1 atmosphere per 760 torr. And so putting that into ATM instead, right, our pressure is 0.93184 atmospheres. Again, just 3 sig figs here because our pressure in torr was also 3 sig figs. But so now, right, we have our pressure. We can also find the volume and the temperature from the question itself. I'm not going to walk through all of the conversions for that step, right? But so putting everything into my N equals PV over RT equation, I have the following. So I have my pressure as 0.932 atmospheres, I have the volume as 0.155 liters, and then I have the temperature as 295 Kelvin. And so when I solve there, I got 0.00596 moles, or choice B here. But so right, this is kind of similar to what you'll be doing in lab with the magnesium and hydrochloric acid lab, right? So we're going to kind of take into account some of the assumptions that we kind of skipped over in our earlier gas collection experiment, right? In the magnesium and hydrochloric acid lab, we're instead going to really account for like the atmospheric pressure and how that equates to the pressure of our gas in our little collection tube. And then we're also going to really account for, right, the partial pressure of that mixture of gases. Because even though, right, our reaction may produce just one type of gas, in reality, the water itself also contributes to the pressure there. And so we want to take into account those partial pressures. But so please let me know if you have any questions, and I'm always happy to help.